All right, let's dive in. Have you ever heard of the Goldilocks problem in AI? It's this huge central puzzle in all of machine learning. Seriously, it's all about finding that perfect balance, you know? How do you get a model to learn just enough, but not too much?
So you gotta wonder, right? How do machines actually learn to predict the future? I mean, it's not some kind of magic crystal ball. It's actually a lot like how we learn. They study a ton of examples, they look at all this past data, hunt for patterns, and then use those patterns to make some really smart guesses about what's coming next.
Okay, to really get a grip on this, let's use a super simple classic example. Imagine you and I, we're running an ice cream shop, and we've been keeping track of our sales, right? We know exactly how many cones we sold on hot days, cool days, you name it. Our mission is to build an AI model that can predict our future sales just by looking at the weather forecast. Seems pretty straightforward, yeah? All right, attempt number one. We're going to start with the simplest, most basic approach you can think of. We're going to tell our AI, hey, just find the most obvious, simple pattern you can. We'll call this our too cold model. And what does it do? It draws a perfectly straight line right through our data. It learns one simple rule: hotter weather equals more ice cream. And, well, yeah, that's kind of true, but just look at it. That straight line, it misses a ton of our actual sales data. It's like a student who crams for a test and only learns the big general idea, but completely misses all the crucial details. It's just not good enough. So this specific kind of failure, it has a name. It's called underfitting. The model is just too simple, too cold to really understand the real story in our sales data. And if it's bad at explaining the past data we gave it, well, you can bet it's going to be just as bad, if not worse, at predicting the future. Okay, so attempt one was a total bust. Let's scrap that. So what do? We do what anyone would do. We swing to the complete opposite extreme. If too simple was the problem, then maybe super complex is the answer. Let's call this our too hot model. This time we tell our AI, listen, I want you to be a perfectionist. I want you to hit every single data point we have from the past, no exceptions. And wow, it delivers. It creates this absolutely wild, curvy, squiggly line that perfectly weaves through every single sale we've ever recorded. It looks amazing, right? A masterpiece of precision. But here's the catch. This is like that student who doesn't actually learn the material for the final. Instead, they just memorize every single answer from the practice test, including all the typos and the random noise. And that brings us to the flip side of the coin, the other huge pitfall, overfitting. See, the model didn't learn the underlying pattern of sales. It just memorized the data, noise and all. So yeah, it gets an A+ on the practice test, our old data. But the second we give it a new day, a new temperature it's never seen before, it's going to completely freak out and make a ridiculously bad prediction. It has zero ability to generalize. And really, this gets to the absolute heart of machine learning. A model acing its training data? That's just practice. It's like winning a scrimmage. The real game, the only test that matters, is how it performs on brand new, unseen data out in the real world. That's it. That's the whole ballgame. So let's just put these two side by side for a second. Our too cold underfit model, way too simple. It completely misses the real pattern. The too hot overfit model, way too complex. It doesn't just learn the pattern, it memorizes all the random noise too. And the end result for both? They're both terrible at predicting the future. And that's kind of the whole point. They're just two different ways to be wrong. Okay, so if too cold is a failure and too hot is a failure, then how in the world do we find what's just right? Well, the answer is in understanding that there are these two competing forces at play, two different kinds of error that are always in a tug of war. First up, we have what's called bias. The easiest way to think about bias is as the error of simplicity. It's like the model's stubbornness. It's the error you get when your model makes assumptions that are just way too simple to reflect reality. Remember our straight line, underfit model? It was so stubborn in its simplicity that it couldn't see the real pattern. That, my friends, is a model with high bias. And on the other side of that tug of war, we have variance. Now, if bias is stubbornness, then variance is the error of complexity, or the model's nervousness. It's how jumpy and sensitive the model is to every tiny little fluctuation in the data it trained on. Our crazy squiggly line model that memorized everything, it was super nervous, reacting to everything. That's a model with high variance. And this right here, this is the fundamental problem, the bias-variance trade-off. On one side, you have simple models. They're not nervous at all, low variance, but they are super stubborn, high bias. On the other side, you have complex models. They're not stubborn, low bias, but they are incredibly nervous, high variance. As you try to fix one problem, you almost always make the other one worse. It's a constant balancing act. So this constant push and pull between bias and variance, that's the whole key. Finding that Goldilocks, just right model. It's not about trying to get rid of bias completely or getting rid of variance completely. That's impossible. It's about finding that perfect, delicate balance right in the middle.
Now this chart, this is maybe the most important idea in all of practical machine learning. Seriously, what we're looking at is the model's total error plotted against its complexity. And what you see is this perfect U-shape. See, over on the left, with simple models, the error is really high. Why? Because of bias. Then, as we make the model more complex, the error drops and drops and drops until we hit this magical point at the very bottom, the sweet spot. If we go any further, if we make it too complex, the error starts to climb right back up again, and this time it's variance that's killing us.
So you see, the goal is not to get bias to zero. It's not to get variance to zero. You can't. The one and only goal is to find that one specific level of complexity that puts you at the absolute bottom of that U. That little valley right there, that's the promised land. That's the lowest possible error you can achieve. And that's it. That's our just right model. That's the Goldilocks solution. It's complex enough to actually capture the real pattern in our ice cream sales, but it's simple enough that it doesn't get sidetracked memorizing all the random, meaningless noise. This is the model that will actually work when we put it to the test in the real world. So why do we care so much about this? I mean, it's just ice cream, right? Well, no. This whole bias-variance trade-off thing, it's not just some cute little story. It is the core challenge in pretty much all of machine learning. It doesn't matter if you're building an AI to predict stock prices, to recognize faces in a photo, or to power a chatbot. Every single time, developers are fighting this exact same battle, trying to find that perfect sweet spot between a model that's too simple and one that's too complex. Which kind of leaves us with this big, fascinating question, doesn't it? If the simplest models are too stubborn and the most complex models are too nervous, then how do we teach an AI to be wise, to find that perfect middle ground? Honestly, figuring that out, well, that's the quest that's at the very heart of building truly intelligent machines.